Greetings, my name is Steve, and today I'm going to be presenting a project I've worked on with my advisor, Dr. Anoop Lamishani. Particularly, we will be talking about solving partial differential equations using radial basis function interpolation. Here on the bottom left of the slide, I've put my contact information. If you have any suggestions or questions about the presentations, please feel free to reach out to me at this email address. Before diving into the content, I wanted to give you a brief overview of what we'll be talking about. In the introduction, we'll look at the motivation for the project, a current modeling problem in which PDEs are being used, and conclude that section by presenting the research goal. When discussing the method, we'll look at a general form of the boundary value problem that we will look at in later examples, provide enough of the theory behind the method of approximate particular solutions for others to be able to implement the method, look at some radial basis functions in the particular solutions, and outline a set of steps for others to follow when implementing the method in a computer program such as MATLAB. Two of the examples we will look at are one is mainly intended just to outline the process, and it is a Poisson problem. And the second one is a little bit more complicated domain in PD to see how the method can be adapted for more realistic problems and to verify the solution is still accurate. Finally, we will conclude by discussing shortcomings as well as what the findings mean. Why is being able to find an accurate numerical solution for PDEs important? Well, PDEs are used in a variety of fields. For example, I've listed physics, biology, and finance here to name a few. And while we focus in an entry-level course on being able to obtain an analytical solution to the PDE, in application, finding a numerical solution is often sufficient or the only possibility. A variety of numerical techniques have been developed. Some that you may be familiar with are the finite element method, finite volume method, and finite difference method. However, we will focus on a class of numerical schemes known as radial basis function collocation methods. Particularly, we will look at the method of approximate particular solutions. One of the benefits of this method is that it is a mesh-free method, meaning that the nodes need not lie on a structured grid. As we'll see in the examples, this benefit can be obtained without forgoing the accuracy of the solution. All of us are aware by this point on what impact COVID-19 has had on our lives, and I suspect many of us have read or even worked on papers in which mathematical models are being used to try to understand the dynamics of the disease. Many of these papers are using compartmental models such as the SEIR. However, there are some papers in which PDEs are being used, such as the example presenting here. This model was developed by researchers at the University of Arizona State, and the idea behind it is rather than just seeing how the number of cases is changing over time, to try to answer interesting questions such as what effect does different geographical and social factors have on the number of cases in Arizona. While I present this method, they do use a different numerical approach to solving the PDE, but I think it's an interesting example worth looking at. With that, we come to our research goal. We sought to review the existing literature to synthesize findings and outline an approach for implementing the method. This is the general form of the boundary value problem that we will see in later examples. To clarify our notation here, L is any linear differential operator, omega is the interior of our domain, del omega is the boundary of the domain, and we'll use the capital delta to denote the Laplace operator in 2 dimensions, as shown here on the bottom of the slide. Also note the functions f and g are stated or known functions. To solve the PDE using the method of approximate particular solutions, we're going to suppose the unknown function can be approximated as this linear superposition of the particular solutions, which we're calling psi sub m. When I say psi sub m is a particular solution, I really mean that it's the solution of this differential equation shown on the bottom of the slide, where the right-hand side is any radial basis function of order m of our choice. Note psi is a function of the distance between points, which we can easily compute using a tool such as MATLAB. In this approximation, the only unknown then are these sets of coefficients, the a sub j, which by substituting this into the problem on the previous slide and imposing the condition that the value on the left-hand side must equal the value on the right-hand side, we can solve for these coefficients uniquely. A variety of different radial basis functions have been used to solve PDEs. We will look at four: the multi-quadric, oscillatory, conical, and Gaussian. The second column of the table is the expression for the mth order of the radial basis function, if there are different orders. And the third column here is the mth order particular solution. Two things I want to point out about this table is that the conical is the one of the four that does not depend on a shape parameter value c. And although in expression for the mth order particular solution of the oscillatory radial basis function has been derived previously, we present in this table only the order being used in examples to make the table easier to read. How do we go about implementing a computer program such as MATLAB? First, we'll generate equally spaced points in the domain. Second, we will calculate the distances from interior nodes to all collocation points, as well as the distance from boundary points to all collocation points. Third, we will use those distances to form the matrix A by substituting our approximation into the left-hand side of the PDE and boundary condition and evaluating at the appropriate distances. Fourth, we'll form the column vector B using the known functions on the right-hand side. On the right-hand side of the PDE and boundary condition. 5, we will solve the matrix equation AX equals B for the unknown coefficients X vector. And 6, we'll verify the accuracy of our approximation using the root mean square error. Our first example is a Poisson problem with Dirichlet boundary condition where the domain is the unit square. As I mentioned a few slides ago, delta here is the Laplace operator in 2 dimensions. Generating collocation points in a unit square. When the domain is simple like a square, this process is straightforward. For the interior nodes, we use the interval 0 to 1, not inclusive of the endpoints, along with the lin space and mesh grid functions in MATLAB to get our grid points on the interior of the square. We put those into a matrix of interior nodes 0, 9, 5. As for the boundary points, the approach that we take is to think of each individual side of the square. For example, in line 8 here, we're going to let the x value go from 0 to 1, fix the y value at 0, and use the mesh grid and lin space functions again to get points on the line segment from the origin to the point 1, 0. We use a similar approach on lines 11, 14, and 17, put those into a matrix of boundary points, and combine the interior nodes and boundary points into a matrix with all of our collocation points on the final line. Here we have a confirmation that our approach has worked. The blue dots are the interior nodes, red asterisks boundary points. To be able to solve a PDE using the method of approximate particular solutions, we need to be able to quickly compute the distance between two sets of points. Since both of our examples, the domain is two-dimensional, we create a function specific to this scenario. If we suppose the input matrix DS is an n by 2 matrix, the other input is a matrix C, which is n by 2 of coordinates. The output of this function is an m by n matrix where the entry in the ith row in jth column contains the distance from the ith coordinate in DS to the jth coordinate in C. To construct this function, we begin by separating the x and y values into vectors, and then we rearrange these vectors to be m by n matrices such that we can subtract the jth x coordinate from C from the ith x coordinate of DS, and we do the same for the y values. Once we have done this, all we need to do is plug into the distance formula. After generating collocation points and creating a distance matrix function, the majority of the work is done. On lines 2 and 5, we're finding the distance from interior nodes to all the collocation points. Similarly for the boundary points here. Then we can use those distances in line 10 to form our matrix A. We'll use the fact psi as a particular solution. So when evaluating the left-hand side of the PDE, we're really evaluating our radial basis function at interior distances and some value of the shape parameter. Since we're using the Dirichlet boundary condition, the bottom portion of our matrix, we have the particular solution evaluated at boundary distances. Line 13, we form the column vector B using the known functions on the right-hand side of the equation. Lastly, solving for the unknown coefficients, here using MATLAB's p-inverse function due to the matrix A being close to singular. Now we have our numerical solution. We just need to see whether or not it's accurate. To do so, we use the root mean square error as it is defined here on the top of the slide. We can find test points in a unit square quite simply using MATLAB's rand function. We then find the distance from those points to all of our collocation points, and all that is left at that point is to evaluate our analytical solution, our numerical solution, and we plug those values into the root mean square error formula. Here's the verification that what we have done has worked, where the green asterisks are just used to emphasize that the test points that are the red dots are falling within the domain. In this table, we have the root mean square error versus different values of the shape parameter. It may seem odd how we've chose C equal to 1.6 here, but this was intentional because previous researchers had found that this was about the ideal value for the shape parameter for the multi-quadric radial basis functions, but our findings do not necessarily confirm that this is true. More importantly, we see that each of the radial basis function provides an accurate numerical solution for some choice of the shape parameter value. However, it is clear that the choice of this value is not trivial. Specifically, if you look at the Gaussian radial basis function, the solution is accurate when the shape parameter is 1, but increasing or decreasing this value and the accuracy of the solution deteriorates quite quickly. In example 1, we got to see the process, but the problem was quite simple. So the idea here is just to see a little bit more complicated PD and domain to see how the method can be adapted to solve these kinds of problems, as well as verifying that the solution is still accurate. We have an inhomogeneous modified Helmholtz equation. Dirichlet boundary condition will fix lambda equal to 10, and the domain here is a hypocycloid of 4 cusps defined by the parametric equations at the bottom of the slide. What changes? The PDE and the domain are more complicated, but the process is exactly the same. What is different in how we execute these steps comes mainly when we're generating the collocation points and the test points. The other main change is that the matrix A must be slightly adjusted. Namely, before we were just evaluating the radial basis function in the upper portion. Now we're going to have the radial basis function minus lambda squared times the particular solution to account for the new left-hand side of the PDE. Generating collocation points in the hypocycloid. The boundary points is still pretty straightforward. We define a parameter interval in line 1 here, then we just use the parametric equations. I'm sorry for the wrong line. We just use the parametric equations to get the x and y coordinates and store these into a matrix of boundary points. As for the interior nodes, it's requires a little bit more thought, but still pretty straightforward. Our approach is to think of a square enclosing the hypocycloid, and we can get grid points in this square. Once we have those grid points in line 12 here, we use MATLAB's in-polygon function to get 2 logical matrices telling us which of these grid points are interior or on the hypocycloid. In lines 15 and 16, we use these logical matrices to assign the appropriate x and y values to a vector and put those into a matrix of interior nodes, which we combine with the boundary points to get all of our collocation points on the final line. This is a verification that our approach has worked. The blue dots are the interior nodes, red asterisks boundary points. The remaining steps, or the other steps, had remained the same, so all that is left now is to generate test points and verify the accuracy. This is slightly more complicated than finding the interior nodes, since these points need to be random, but the idea is still the same. We'll think of some square that encloses the hypocycloid, but now think of that larger square as 4 smaller squares, 1 in each of the 4 quadrants. By doing so, we can use MATLAB's rand function and multiplication by a scalar to reduce the problem to the same as it was in example 1. And we get our random test points in each quadrant. And then in line 14, use the in-polygon function to get a logical matrix telling us which one of these test points are interior of the hypocycloid. Using this logical matrix, then we assign the appropriate x and y values to a matrix of test points. This figure is showing that our approach again has worked. The green is denoting the boundary of the domain. The red dots, which do appear to be random, are the test points. Finally, in this table, we present again the root mean squared shape versus different shape parameter values. The noticeable finding is that all four of the radial basis functions are still providing an accurate numerical solution for some choice of the shape parameter value. And the idea that we saw previously that that value is not, the choice of that value is not trivial, again seems to be true here. In that respect, radial basis functions that do not depend on the value of the shape parameter, such as the conical, may be seen as ideal by those looking for an accurate approach, but one that requires minimal effort. So what can we conclude from this research? Well, first of all, I think it's important to recall the research goal, namely to bring together the previous findings in a way that made it simple for others to implement the method in projects that they're working on. That being said, a couple important issues such as choosing the optimal value of the shape parameter and an order of the radial basis function at which we obtain the most accurate numerical solution did not receive a sufficient amount of attention. However, we use a range of values for the shape parameter to try to lessen the severity of this shortcoming, and it must be remembered there are radial basis functions that do not depend on a shape parameter value. Even with this shortcoming, our findings indicate the method of approximate particular solutions is a simple and effective method for solving partial differential equations. With that in mind, we hope this project will inspire those working on projects in applied mathematics, the sciences, engineering, and any other field in which PDEs are being used to try implementing the method in the projects that they are working on. Thank you for listening to my presentation, and I will conclude by sharing the main sources that were used. I hope you enjoy the remainder of the conference.